Buckle up, because it's hands-on time. We said an image is a bunch of layers, we read the manifest file, we stack them up, then we throw in some magic to make it all look unified. Well, you know what? To get an image in the first place, we have got to pull it. And I think probably the easiest way to do that is with Docker image pull. And we'll have Redis. Now, if you're on a Windows machine, I recommend maybe Microsoft/.NET. Anyway, each of these pull completes here is a layer, and it's the same on Windows. Now then, there's actually no such thing as an image, at least not as a single blob or object. You see, an image is actually a bunch of independent layers that are very loosely connected by a manifest file, which I know is at odds actually with the way we always talk about them as if they're a single blob, but they're not. Under the covers a bit, the manifest file, which we sometimes call the config file, right? But as you'd expect, it describes the image, like its ID and tags and when it was created, but importantly, it also includes a list of the layers that get stacked and how to stack them. Now these layers are blissfully unaware of the bigger image. They're just a bunch of files that are what they are, an independent layer. They have no clue that they're going to be stacked up and made into something bigger. So what I mean by that, right, is that one layer in an image has no references to other layers. All of that's done in a manifest. And I think we get an idea of this actually with the pull we just did. I mean, look, we're not pulling the image, so to speak, as a single object with a single progress bar. It's obvious that we're pulling individual layers. And it looks like 6 of them. Anyway, behind the scenes, the pull command generating an API request to the Docker registry API on a registry somewhere. Now Docker's a bit opinionated about registries, so unless you tell it something else, it's going to assume Docker Hub. Okay? Well, pulling an image is actually a 2-step process. Get the manifest, pull the layers. Now the manifest's a bit interesting, right? We've got this push towards multi-architecture support and content addressable storage. One's about supporting a single image across multiple architectures, maybe x86 and ARM and PowerPC or whatever. And the other's about using cryptography to guarantee we get the images we asked for. Anyway, step 1's getting the manifest. Now, the client first looks for something called a fat manifest. And that's like a manifest of manifests, right? Basically, it's a list of architectures supported and a manifest for each of those. So if your architecture's on the list, it points you to the image manifest that you need. Well, for us, we're on Linux x86 or AMD 64 or whatever. Okay, yep. So for us, we get the fat manifest, have a look to see if there's an entry for Linux on x86, and if there is, we go get the image manifest for that. So I suppose getting the manifest's a bit of a 2-step process these days. Get the fat manifest first, then get the image manifest for your architecture. Once we've got that, we parse it for the list of layers, and we download them from the registry's blob store. Which is what we saw here with the pull. Now then, we mentioned content addressable storage. So back in the day, Docker didn't hash its images, and there really wasn't an easy way to know if the image we got was the image we asked for. Well, that's obviously not good, especially when most of us are pulling our images across the internet. So, problem. Well, solution, and thanks a ton to the community and OCI, but in Docker 1.10 we got content addressable storage, which at a high level says, okay, every layer has got a bunch of files and stuff inside, so I tell you what, let's grab a hash of all that content and use it for the image ID. That way we can say, okay registry, give me the image with this particular hash please. We download it, run the hash again and see if the two match. And in one fell swoop, we have got a way more secure storage model. So you'll see in the image manifest here that we're referencing stuff via a hash. These are the layer IDs. The syntax is just algorithm, SHA-256 in this case, colon, and then the hash in hex. Anyway, we get the manifests and we pull the layers, and hey presto, we've got the image on our host. And actually we can see the hash if we want. Okay, right. Anyway, where are we? Okay, we've got our layers, they're linked and stacked thanks to a manifest. And behind the scenes, we've got some crypto goodness giving us immutability. Now then, behind the scenes, there's a storage driver pulling together all of this layering. For us, it is the AUFS driver. Oh, and most of our images and container stuff is going to exist somewhere here in varlib docker. On Windows, this is going to be C program data docker, and your storage driver is always going to be Windows filter, though those could be famous last words. But here on Linux, right, there are a ton of storage options. AUFS is the oldest driver, and you still see it everywhere, but personally, I think Overlay 2 is the future. Now then, layering pretty much works like this. There's a base layer at the very bottom. I tend to think of this as like the OS layer. It's the one that's got all the files and objects that build a basic OS, like Ubuntu or something. In fact, let's assume it is Ubuntu, right? But don't forget, when you run this image as a container, it's going to be using whatever kernel you've got down here on your host, and that could be SUSE or CentOS or whatever. So all that's actually making this base layer here Ubuntu is things like, I guess, the usual Ubuntu file system layout and maybe a few common Ubuntu tools. So it is totally possible to be running a CentOS Docker host with Ubuntu-based containers on it. Not Windows, mind you. So it's got to be Linux on Linux or Windows on Windows from a kernel perspective. Now, I'm not talking about Hyper-V containers here. Anyway, look, that container is going to be using whatever kernel your CentOS OS here is running. But the file system that likes inside of it are going to feel like Ubuntu. Mental maybe, but it works. Then, on top of the base layer, we stack more layers. Things like your app code and the likes, right? Now, I know this is a bit simplified because I hate PowerPoint, but it gives the picture. An OS at the base layer with files and libraries and stuff, copy in some app files as another layer, I don't know, maybe add another layer of updates later, and the storage driver waves its magic wand, abracadabra, and the layers disappear, and we're staring at what looks like a single unified file system. Fabulous. Now then, each of these layers is represented in a directory in the file system under varlib docker and then your storage driver name. For us, it's AUFS and then diff. Windows, that's going to default to C program data docker Windows filter. Okay, 6 directories, and funnily enough, 6 layers. Simple, right? Maybe not so much. You see, since we've got this fancy new content addressable storage model, there's no easy way to match the layer IDs with their respective directories on the host. And it's definitely annoying. Well, I reckon this one here with the most objects is probably the base layer. Right, so that right there is the contents of the base layer of the Redis image we just pulled. And if you know your Linux, you're going to know that we're looking at a root file system. And that's what we said, right? The base layer of an image has all of the OS files and directories. Then these other layers are going to have like the app code and the config files and stuff. In fact, what's this one up here with only 4 objects in it? Oh, it's got a couple of hidden objects as well, right? That's where the 4 comes from. But Etsy, what's been added in here? Okay. Looks like someone's maybe been updating the users and groups for the image. So if we go Docker history Redis, now don't be put off by this, right? I'll explain it in a second, but I'm looking for something here that, okay, I bet it's this. See how this command, and this whole list here, right, is commands and stuff that build the image, but this command here is adding Redis users and groups. So that's the one that's going to have created this layer up here. Cool. Now, a few things about this Docker history output. First up, just ignore this column here, right? There's nothing wrong. It's just that the command's older than the new storage model, so it gets a bit confused. Anyway, the operations here are a history of how the image and its layers were built. This here at the bottom right is adding all of the file system objects. Then any other line that's got a non-zero value at the end here will have created a new layer. Anything that is 0, well, that probably added something to the image's config JSON. So I reckon we should have 6 non-zeros here. 1, 2, Okay, well, we've definitely got 6 layers. Okay. Okay. Right. This one here. It's creating a directory and setting some ownership. So I'm guessing, I don't know, maybe it's produced such a small layer that it's got rounded down to 0, probably 10K or something. I don't know, but the point is, right, when building images, some of the things that we do create new layers, and some of them add stuff to the image config file. This here's a list of everything that built the Redis image, and we can see these obviously created new layers, whereas things like setting environment variables and exposing things like network ports just add config to the image's JSON. Now, I want to show you one last thing before we move on. Running Docker images inspect on the image gives us its config and its layers. So at the bottom here we see the layers, yeah? But these are their content hashes. Now, sadly, they don't match up with the directory names or the image IDs shown in a pull. But we see 6 layers and these are their hashes. If we look further up, we see other stuff that makes up the image. Working directories, environment variables, network ports, you name it, right? But that, I hope, is probably enough for now. So a bunch of layers with files and stuff in them, stacked on top of each other and unified by a storage driver according to instructions in a manifest. Then we start containers from them. Multiple per image if we want. We pull them with a Docker image pull, inspect them with a Docker image inspect, and delete them, oh yeah, with a Docker image RM like this. And it's gone. Including all of the files in varlib docker aufs diff. Pretend we didn't see that. Now this end bit of the directory right is different if you're using another storage driver obviously, and on Windows remember it is all under C program data, Docker, Windows filter. Anyway, last but not least, an image is basically a manifest and a bunch of loosely coupled layers. Alright, let's switch tack and talk about registries.